Good afternoon, ladies and gentlemen. It's a real pleasure to introduce to you Dr. David Farrusseng. Next week, in July the 11th, he will turn 44, so it makes him really eligible for this award. And he grew up in the southern part of France, studied in Montpellier. Then there he also obtained his PhD, moved for a postdoc to Germany in the group of Friedrich Schütt in Mulheim, the Max Planck Institute, returned to France where he became a CNRS researcher in Lyon, grew up there as an independent researcher and has made a career in the design of porous catalytic solids with an emphasis on metal organic frameworks. Lately, he also has been shifting his attention to metal nanoparticles. He has been the recipient of the French Catalysis Award. He has authored more than 140 papers, 17 patents, of which one has been applied. And I think he has now a very intriguing title, so I invite you to give your talk with the title Catalysis Inside the Box. Congratulations again.
Can you hear me? Okay. I knew that this moment would come, and I shall say that I'm very moved. It's such a big honor to be here today and to get this prize. I would like to thank Avelino Korma and the IACS committee members, and I would like also to thank Professor Canley and the ICC committee for the kind invitations. By the way, Professor Canley got the same prize a few years ago in Paris, so I hope it's just not a payback from China to France, this award. It's such a prestigious when you see the fantastic career of Professor Canley. So I take this award not only as an acknowledgement of my past achievements, but also as an encouragement to take risk in my research. Before starting my lecture, I would like to thank a few people and introduce you the city of Lyon. I would like to thank Professor Anne-Jules and Christian Guizard, my former supervisors in Montpellier, who, let's say, guided me on zeolite membranes, and you will see the link with the today's talk. I would like also to thank Friedrich Schütt, my supervisor at the Max Planck Institute, and Claude Mirodatos, that many of you may know. He has guided my first steps at CNRS. I would like also to thank my team here. It's a picture we have taken a few days ago in the sunny Lyon. Without them, of course, I wouldn't be here today. You can see here Lyon is a beautiful city. Lyon is located at 2 hours south of Paris by fast TGV, fast train. And if you go south to by train, you will find the French Riviera. So Lyon is a very nice place to be if you want to visit Lyon. The city center is actually beautiful. It is the patrimony of UNESCO. And if you want to do business, you can see it's also a business-friendly city, the first in France. Lyon is a city of art and culture. One of the largest events is the Festival of Lights in Lyon. It's originally a religious fest, but today it's now become common. Children put every December 8th candles and lights at the windows, and all of the city is illuminated. It's a fantastic time. Now it has become a bit more sophisticated. All the facades of the buildings are illuminated by lasers and show. In memory, I think, to the brother Lumières, who have discovered the movies, and the first movies have been recorded in Lyon, actually. Also, if, well, you know, wine and food is part of the culture in Lyon. You may recognize Paul Bocuse. Him and other colleagues have set the rules of the nouvelle cuisine, which is more delicate and lighter, with an emphasis on the presentations. It's also well situated. Lyon is well situated for the wine region. Lyon has a very long-standing relation with China through the Institut Franco-Chinois, and many important Chinese people were educated here, including former President Deng Xiaoping, who was student there, and recently we got the visit of the current president of China. Lyon is also called the Valley of Chemistry. We have many oil and chemical companies settled there for many years, and we have also very large research centers like IFP. You can see high throughput facility here, or CNRS with new infrastructures, large buildings, and cutting edge tools. We have a very beautiful NMR park and transmission microscope. You're gonna see many pictures of this one today. Everything, all of that would be nothing without smart people and pioneers. You can see here the pictures of Dr. Yves Chauffin, employee of IFP, who got the Nobel Prize in 2005 for his research on metathesis mechanism. And Yves Chauvin said often to the youngest that we must take risks in our research. It's sometimes very frustrating, but at the end, it pays off. And here it brings me to the title of my conference. Indeed, many of you may wonder the meaning of the title, Catalysis Inside a Box. So in fact, it's quite simple. The box is a zeolite single crystal silicalite 1, so aluminum-free ZSM5, if you wish, and inside it is hollow. You're gonna see that on the movie if I'm lucky. Yes. So this is the crystal, and inside we have removed the matter to make them hollow. So you have a huge cavity, and inside we're gonna put metals, and eventually these metal particles will collide and form a unique single particles encapsulated in this zeolite membrane. And with this new system in hand, I'm gonna revisit key aspects in catalysis, so 4 different aspects: activity, deactivation, size selectivity, and diffusional limitations. So activity, well, it's of course very important to design, but also to make efficient catalyst. And for that, you have 2 components. The one is the surface compositions of the metal particles. I will address here only activity of metal catalysis. So you have to control the composition of the surface and also the size of the nanoparticles. If you do so, if you are successful, then you have to prevent that nanoparticles, which are, when they are very small, they diffuse at the surface and eventually collides and then sinter together. Then you are losing a lot of surface and activity. So I'm going to show you how we can prevent these particles to sinter by using the zeolite as a shell, if you want. Then I will move to the size selectivity. Size selectivity is very well known in zeolite catalysis. Because of the mass of the pores, you can discriminate reactants of different size. This is not the case in metal catalysis, where all the reactants get access to the metal surfaces. So I will show you with 3 examples how we can, let's say, add a selectivity function, a size selectivity function in metal catalysis. And briefly, I will mention diffusional limitation, because as you know, the diffusion of substrates in the pores of zeolites are very slow, and it may turn that the activity that you measure is not the activity of the metal, but the rate of diffusions of the reactants in the zeolites. But before addressing the activity, I want to show how we make these hollow zeolites, like that. It's in fact very simple. You start with silicalite 1 crystals, if you wish, aluminum-free ZSM5, and then you treat them in the TPAOH, so tritiylpropylammonium haloxide solution at high concentration for 3 days, and you're gonna see this hollow crystals, you can recognize here the hexagonal shape here. This is the top view, you have it here, and the square shape, this is the side view here. And every of them are hollow. When we saw that, we could hardly believe it. And I can give you the picture of the synthesis. We know that at the core of the crystals here, it's not so well crystallized, I would say. We have many silanol defects which are prone to dissolve in basic conditions. And when this silicate diffuses, eventually it goes to the surface, then it meets the tetrapropyl ammonium, which is the template which helps to the crystallizations, and immediately recrystallizes at the surface. And along with the synthesis time, you have less and less matter inside, and all the matter has been moved to the exterior and recrystallized at the interface, which yielding a zeolite crystal, which is a bit larger than the initial one. So here, 100% of the silicate which were inside has been recrystallized at the external surface. And you can see here on these STM pictures that all the crystals have the same size and all are hollow. It is very important to see the homogeneities. They have all the same cavity volume, which will be used in the next slides as a nanovessels, as a nanoreactors to control the size composition of the nanoparticles. So all the same size, all the same cavity volume. It is also possible with the variations of the template to make not only not a large cavity, but smaller cavities which are interconnected to each others, like this here, if you want to see the scheme. At this point, it's very important to know whether this cavity, either the big one or the smaller one, have directly access to the exterior of the crystals, or if they are separated by the thin membrane here, like around. And we can learn that by looking at the isotherms, absorption isotherms of nitrogen at 77 K. You can see the three isotherms for the three samples: the plain zeolite, the single hollow zeolites, and the multi-hollow zeolites. Here you can see that they are all microporous. And you can see obviously here a large hysteresis, which arises from the capillary condensations of the nitrogen inside the pores here. And what is important to take note is that the closure of the desorption isotherms close at 42, which characterizes a phenomenon called cavitations. And it means that when a nitrogen molecules here want to go out of the crystal, it has to cross zeolite membranes. In conclusion, there is no defects in this zeolite shell. We have a perfect zeolite membrane, 3D zeolite membranes. This is also the same for this multi-hollow sample. So now with this, let's say, nano vessel, I will show you how we can make the nanoparticles and how we can control the surface composition and also the size of the particles. And I would like to give you first, why we want to do that. It's important, of course, in metal catalysis to control the surface composition, because the maximum, as said Paul Sabatier, the maximum rate of the catalyzed reactions is achieved when the association between catalyst and reactants has a medium stability. So it's important to well design the catalyst before. This principle have been put in, let's say, kinetic expression later on, and the let's say the strength of adsorption between the reactants and the surface can be now computed or described by DFT. Here it is an example of a reaction of methanations of CO. So I will go not so into the detail of that, but basically what it says is that for palladium and platinum with very weak energy of dissociations, the reaction rate of methanation is low. And On the other hand, for rhenium of iron, okay. Here. Shall I remove that? Can you give me? Sorry about it. Can you hear me better now? Okay. So when you have a low interactions with metal particles, you have a low activity. On the other hand, for rhenium or iron, if it is too strongly absorbed, also you have a low activity. This is only for medium stability here metals that you get the highest activity. What is also important to remember is that if you select two metals that are on the different side of the volcano curves, mix them together, also you get very high active catalyst. The conclusion of that is we have now models and computational tools to design libraries and many candidates, catalytic candidates. So there are plenty of ideas to be tested, okay? The second point is we know also the dispersion curve as a function of the size of the nanoparticles. If you want to have a decent activity, so to say, it's better to have catalytic nanoparticles below 10 or 15 nanometers. So basically, we know how to design very active metal catalysts by the help of supercomputing and modeling approaches. So it is no longer an issue to design a metal catalyst. It's no longer an issue for testing either. We have parallel tools. We can test bunches of catalysts in a couple of hours or days. The bottleneck is actually to make the catalyst with the high control of the surface compositions and particle size composition. For example, we could fix metal compositions like 50% gold, 50% silver, and vary the particle size, or fix the particle size, so to say 8 nanometers, and have many different bimetallic of different compositions of this particular size. This is actually a challenge to find a generic process to vary independently the metal compositions from the particle size, everything else being the same. If you change the support, you change everything. And I'm going to show you how we can use this nano vessel as nanoreactors to make those particles. So we start from silicide one, we impregnate. In this case, we're going to do the gold as the first example. We impregnate with gold solutions. We have, after drying, we can see smaller with tiny particles inside the crystals where there are the maximum of defects. And then we apply the dissolution recrystallization process. We make empty the zeolite. And surprisingly, what we found is that in each cavity, we find one single particle in each cavity. We could hardly believe it when we saw that for the first time, actually. And what happens is that we have the particles here, and progressively the matter is going out. The particles, gold particles, sinter together, and they cannot escape because the size of the nanoparticle are much larger than the pore opening of the zeolite, which is only a few angstrom. And we can see in these pictures that for each zeolite cavity, we have one single gold particle of very with a very homogeneity in the size distributions. You can see here at high magnifications the thickness here of the zeolite shell, 20 nanometers, and the very high crystallinity of the zeolite shell. We can easily vary the size of the nanoparticles by adding more gold to that. For example, for a gold content of 0.08 white percent, we have 2.6 nanometer, and for 1.2 white percent, we have a size of 7.5 nanometers, and you can see with always a sharp distribution. And we were also surprised to see that there is a relationship between the gold concentration of the solution that we use and the gold particle volume. Indeed, you have to remember that each cavity have the very same volume. So it's like a nano beaker. If you increase the concentration by a factor of 4, you will have 4 times more matter, meaning 4 times more volume. And as it centers in one particle, the volume of the particle will be 4 times larger. And because there is, of course, a cubic relation between the diameter of the particle and the volume, it's easy to control the diameter. And then you can think back, if you want to synthesize a gold nanoparticle of 5 nanometer, which correspond to 65 cubic nanometer here, then you just follow the line and you find that you need a gold solution of 0.13 mol per liter, and then you will get exactly the particle size you want. Then if it's all for gold, it should also work for other metals. And we did it for palladium, for example. In each cavity here, you can find one single particle of very controlled size. We plot here in black, this is the gold content or the gold particle volume as a function of the metal loading. And in red, you can see this is the palladium. So this is, I think, a general rules. And furthermore, it means that if we can control at the same times the gold and the palladium, it means that we can also control the composition of an alloy if we put them together. And this is what we did, for example. This is a cartoon for platinum, sorry. We can control the platinum content, which eventually lead to nanoparticles. If you add palladium, then eventually you will get a PT-PD alloy. So here is the results of that. We start with a single crystal. We do the impregnations of platinum and palladium solutions. And after the heat treatment, this is what you get. So black deposit or black precipitate, which are the metals in every kgs with a PT-PD ratio that correspond to the expected amount. After calcinations, you have more rounded particles, but still not very well, I would say, perfectly rounded. It's only after the reducing treatment that you get a perfectly rounded nanoparticle that we believe it is an alloy. And we repeat that for numbers of alloy and size. You can see that for each cases, we have a very narrow distributions of the particles. And for example, you can see that for this example, we target 8 nanometers as let's say, target size for the particles. But we have here 3 different alloy, gold, silver, platinum, silver, platinum, palladium. So in other words, it is really possible, and this method allows to control independently the compositions of the bimetallic particles and the size. we plot also, this is the plot I showed you before, gold and palladium, and we plot them for all these new bimetallic species. What we found is that for high loading, we haven't found actually the same results. And we found later, after a lot of investigations, that the metal loading, which was characterized by ICP, was in fact wrong, because when we dissolved the samples in basic medium, we got precipitate that cannot be solubilized for the ICP analysis, meaning that all the highly loaded samples where the metal content were underestimated. So we still believe it is following the linear relationship I showed you before. But our concern was not that. Our concern was whether we had actually alloys and the surface compositions of those alloys. So we have made deep investigations of the metal compositions in each particle by IDX. So every white spot here is the particles, and we look at different spots on these particles to look at, for example, the PT or silver ratio, you can see that on one particle it is very homogeneous. And we repeat that for all the bimetallic system we did. So we have done EDX analysis about 20 to 30 different nanoparticles and make an average and statistics here. And you can see that they match pretty much with the ICP analysis here. It means that every particle is composed of both elements that we don't have palladium here and platinum there. They are all mixed together in a very homogeneous composition. We wanted to go one step further and look at the surface composition. It is known that the XPS is the most appropriate technique to look at the surface. But here we cannot do that because the signal is shielded by the zeolite membranes. The XPS cannot cross the zeolite membranes. So in conclusion, it tells you that all the particles are well encapsulated in the membrane zeolite. But still we wanted to know whether we had at the surface both, for example, here in this case, silver and gold, and for that we have selected a CO oxidation which gonna give us a fingerprint of that. So we know from the basic that on here it's gold nanoparticle, and here it's pure silver, and here it's a mixture, it's an alloy. We know that oxygen does not dissociate on gold, and it's a poorly oxidizing catalyst, obviously. While silver dissociates very strongly oxygen, and there is no room here for CO to react. So it's also a poor catalyst for CO oxidations at lower temperature. So it is known that this is for mixtures of 50-50 or 2-to-1 ratio between silver and gold that you get the maximum activity. Nevertheless, if you start with the 50-50% mixtures, because the silver tends to go at the surface because of its surface tensions, all the population of the silver at the surface will be covered by silver. So the bulk composition has to be very poor in silver, so that then you can reach, for example, a 1-to-2 ratio between silver and gold. So this is these compositions that we have targeted in order to have these surface compositions. So we did it here. We prepare gold-silver nanoparticles encapsulated in silicate 1. Again, every cavity is filled by 1 nanoparticles of 8 nanometers. And then we tested that in the CO oxidations. We test first the pure components, the gold and the silver, and you see here both are not active, as I said earlier. But the mixtures, the alloy is, and actually this is a fingerprint that at the surface we have both metals. So we concentrate our investigations on metal catalysis, and we were very proud to see that we had a follower in China, Professor Guo from Dalian. He used the same approach, so our let's say nano zeolite and empty zeolite for the synthesis of nano heteropolyacids. So you see, it's not magic. Everyone can do it, and I think it's a new area to prepare new solids. But that would be pointless if those nanoparticles sinter together. So I will see how we can prevent the sintering by these encapsulations. The first example is on 0.8% of platinum encapsulated in silicate 1, and after a heat treatment at 750 degrees C, quite high, and the hydrogen, you can find hardly any change in the particle size. If you do the same treatment on platinum on silicate, you see a big change in the pore size, particle size from 7 to 17. But that might be not a very harsh treatment. Water is known really to promote more sintering effect. And for this one, we have selected the gold-silver case, and you see here hardly any change after this steaming treatment, whereas in the case of encapsulation in MCM41 that you might think it also prevents a particle to sinter. This is not the case. The MCM is completely destroyed by this quite moderate steaming treatment. But maybe some of you are not yet convinced about the stability of such materials. So we selected the steam reforming of methane in very harsh conditions, 700 degrees C here on the nickel silicalite, with 40% of steam. It's really huge. And look at here the velocity, 500,000 per hour. It's a huge velocity. Here you can see the methane conversion as the functions on the time on stream. You can see an exponential decay, which is due to the sintering of the nickel particles. In this case, here we have characterized the catalyst. You may see here very small nickel particles. In this case, for the nickel, we don't have a single particle, but many smalls that are attached to the surface. And after a while, they sinters. So you see, you lose a factor of 3 in the dispersion, which corresponds more or less to a factor of 3 in the catalytic activity, which is here. So a way to prevent that is to make the small cavities, multi-hollow catalysts, multi-hollow cavities, so that all the nickel particles are really encapsulated and then cannot really sinter or not sinter so much. And you can see here the stability is well maintained for a day. Now I will address that would be a large part of my talk on the size selectivity. Size selectivity is very important in catalysis and hardly achievable in metal catalysis, obviously. And why this is important? Well, if you want to hydrogenate selectively toluene here and not trimethylbenzene, but if they are both present in the medium, well, they will get both absorbed at the surface of a metal particles, this is the surface, and eventually reacts to lead to the corresponding alkanes. If you want to selectively convert the toluene, then you shall prevent the trimethylbenzene to absorb, otherwise you have lost. And I will show you how we can use the zeolite membranes to make this sealing. This example, I would say, is pretty obvious. This one is not. This one is the CO oxidation in presence of ethylene. And if you try in the laboratory, you will have a hard time to make these reactions very selective of CO2 without burning ethylene. Why that? It's because the interaction between ethylene and the metal and CO and the metal are the very same. If you look at the molecular diagram, you find the same, because obviously you have sigma bonding and back donation of the metals. So the type of the bonding are the same, but also the energy of the system are the very same. The dissociation energy of CO and ethylene are the very same, whatever the metals. So how you can do selectively these reactions without the help of another component. And I'm going to show you how we can use the zeolite membranes to selectively convert CO into CO2 without touching ethylene. And here are the 3 mechanisms that I know in the field of zeolite membranes for achieving high separation and high selectivity. And for each cases, I will show one example. The first is obvious, is size exclusion. It is when one substrate is much larger than the pore window of the zeolite. It's obvious you're going to have a size exclusion. The second is called more diffusion-driven selectivity. Here, both substrates have size which are smaller than the pore window, so they are allowed to diffuse in the zeolite membrane, but one is a bit bulkier than the other. That would be, for example, the case of normal alkane and isoalkane. And because so, one will have a diffusion energy much higher, and so will diffuse more slowly through the zeolite. I'm going to show you a way how we can use that for enhancing the selectivity. The last mechanism known in membrane, but not so known actually in the field of catalysis, is what we call adsorption-driven selectivity. This is when, let's say, a substrate, the green one, has a much stronger adsorption energy than another one, and will, so to say, populate all the cavities, and they will not have room for the other component to adsorb and then diffuse. So it's also a size exclusion, and it is favored at either low pressure or at high pressure or low temperature. So I will show you here as well an example. So the first, how we can use the sieving property of zeolite membranes to enhance the catalytic properties. For example, what we want to do is to hydrogenate toluene and not trimethyl benzene, and so we know that prior to that we did some adsorption measurements, and we can see that toluene is able to enter into the cavity, whereas mesithylene or trimethyl benzene not. So if it's true, then we can do a selective hydrogenation. What you can see here is the activity, the hydrogenation activity of toluene as a function of the temperature. And we selected platinum silica as a standard materials. You see here that our platinum encapsulated in silica light one behave the same that the normal catalysts. In contrast, for the trimethyl benzene, you can see that in our catalyst we don't have any activity, whereas for the reference catalyst it is. So actually we have here an example, perfect example of molecular sieving phenomena. The second example here is, as I told you, when the energy of diffusions of one substrate is much higher than the other, and I will address the case of the CO oxidations I told you a bit earlier. So I will show you one reaction, the CO oxidation, very simple, with an excess of oxygen, and then we're going to add propylene, which will poison the surface of the catalyst and eventually then also burnt because of the remaining oxygen content. So here, as an example to show you how difficult it is to make these selective reactions, we have selected silver on gamma alumina. You can see here the conversion as a function of the temperature. Here in black, this is the CO conversion. You can see the light off at about 200 degrees C. Very easy, oxygen conversion level off at 70 because there is an excess of oxygen. Then we have another pictures when we had propylene. You can see that here in this case, the CO conversion developed at 40%, and you wanted here to have it at 100%, and that you start to burn propylene. So it's not what you want. It's a very unselective catalyst. And here is the comparison of our system with the conventional platinum in silica, silicalide. So here the standard it was just an impregnation of platinum solution on a silicalide one. You have particle inside, you have particle also outside, and here is our material, so to say. You can see the CO oxidation, very same for both. Again, in the classical catalyst, what you see when you introduce propylene is that the CO conversion level of at 40%. Basically, the propylene poisons the surface of your catalyst. You can even see a shift of the light-off temperature between 250, from 250 to 300. This is the sign of surface poisoning by the propylene, because they have both the same activity regarding the metals. In contrast, in our case here, you see a bit decrease of the CO conversion, but still reaching more than 90% of conversion. And what we believe is that this is because we have diffusion limitations in the case of the propane oxidation. We have measured both the CO diffusion rate and the propylene diffusion, and we found that there is a difference of, let's say, 2 orders of magnitudes in the diffusion kinetics. So it means that very likely the CO and oxygen cross very fast the membranes, react, whereas for the propylene, it slowly diffuses through the catalytic particles and then reacts with much less apparent kinetic. so to say. The last case is where the reactants are much stronger than the other and push it away from out from the zeolite membrane. And for that, I've selected the case of Fischer-Tropsch catalysis. You can see here a 3% of iron in silicalite 1. So you see here the black spots are the nanoparticles, the iron nanoparticles. In this case, you don't have a single particle again, but many small particles. And it's hard here to say where are they located, these nanoparticles. So we did a tomography analysis. I will try to run the movie. Yes. So the blue is obviously the zeolite cavity, and the red spots are the iron particles. If you look closely, you can find hardly any, let's say, red points either on the external surface, neither in the inner surface, meaning that actually all the nanoparticles are included, are embedded within the shell. All the nanoparticles are, let's say, protected in the shell. It is very important for the catalytic properties you will see here. So this makes these nanoparticles iron extremely stable in the Fischer-Tropsch conditions. We have tested that for weeks and even months under different operating conditions. We have analyzed by TM the nanoparticles before and after, and you could see hardly any change of the size distributions of the iron, which is centered between 3 and 5 nanometers. If you apply the same treatment at iron nanoparticle without any support or just a silicate, then even at such high dispersions, they will completely sinter in the Fischer-Tropsch conditions and lead to very poor activity. But back to the selectivity, right? Here is the list of different catalysts we found in the literature based all on iron, and you can see that whatever the composition, whatever the operating conditions, they all produce CO2. And it is expected because in the Fischer-Tropsch reactions, you produce obviously the oil, the alkanes or C5 plus fraction if you want, and you produce a lot of water. And in a parallel reactor, the CO reacts with the water in a so-called water gas shift reactions to produce CO2. And iron is known as a very active water gas shift catalyst. So it's obvious that we can expect a high amount of CO2 in all type of iron catalysts. Here are the results. You can see first a commercial catalyst, about 78%, 8% of iron, tested at 250 degrees C, 30% conversion, light productions of light hydrocarbons, and you see, as expected, 22% of CO2 and a very high selectivity in the liquid hydrocarbon fractions. For our catalyst, which is only loaded at 3%, doped with copper and potassium at 20% of conversion, what we have is a bit more light alkanes, but look at that, we don't have any CO2. It was really amazing, and we were wondering why we have that result. And it results in a liquid selectivity, in a hydrocarbon selectivity of about 80%. And you can see also that the activity calculated by gram of iron is the same than for the commercial catalyst. If you try to compare with the 3% iron on silica, well, the conversion is so low that you cannot, in fact, look at the selectivity. So we were wondering why we have such selectivity, and it comes from the adsorption property of the zeolite, of the matrix in which is embedded the iron nanoparticle. It comes from here are the water adsorption property, you can see here the water uptake are the functions of the relative humidity. If you take a silicate, whatever it is, it has a lot of silanol groups at the surface, which make it very hydrophilic. You absorb a lot of water, whatever the relative humidity. In NMR, it is known as Q2 or Q3. In our cases, what we have is, in the case of the plain silicalite 1 or the hollow silicalite 1, here in red, we have only Se or Se bonds, and which are characterized at NMR by this Q4, which means that we have a very, very or super hydrophobic hollow silica. We hardly absorb any water, whatever the relative humidity. So we don't absorb water in the cages. And on the opposite, of course, if we don't absorb water, this type of membranes like very much to absorb oil. You can see here the heat of absorptions of the liquid fractions, pentane, hexane, and so on, with a very high absorption strength on the zeolite, much higher than the water. It means that we are here in the case where we have one component which has a much higher absorption strength than the other, and obviously it will push out the water out of the membrane. So either in the scheme of that, we have here an iron nanoparticle embedded in this very narrow and very thin membrane shell. H2 and CO would go across the membranes, react, produce the water and oil, but water and oil cannot be there together for long. They have to separate. Oil and water doesn't like each other. So what will remain in the system, in the pores, this is indeed the oil, and the water will be pushed out. This is the winner here in this case is of course the oil. We have oil and water separation, and this is why I think this reaction does not happen, or very in slow kinetics, because we don't have water close to the iron particle because of the kind of thermodynamic at the local stage. This reaction or the kinetics is very much prevented. Now I'm going to give you a few words on diffusional limitation, because it is known that the diffusion in zeolites is extremely slow, and I want to give you here the worst case scenario, so to say. I've taken the example of the toluene hydrogenation because toluene is a quite large molecules and have hard time, so to say, to diffuse in the zeolite. It has a very slow diffusion rate, while the hydrogenation is a fast reaction. So we are here in the case where we have a fast reaction and a slow diffusion. It's a perfect case to be limited by the diffusion. And how you can estimate that? Well, it's by the estimation of the Thiel modulus that is put it here. Briefly, if you have a Thiel modulus larger than 1, you will be limited by the diffusion. For example, if you have 10, you have an effectiveness factor of about 0.1, meaning that only 10% of your nanoparticle will be active, will work under reaction conditions. Instead, if you are below 1, all the nanoparticles or the particle will work. So how we can estimate that? This is the expression is here. So for the rates, we have measured the platinum on silica. This we could have taken also numbers from the literature. So this is outside, of course, diffusional limitation. This is intrinsic to the platinum catalysis. And for the denominator, we have taken a value of the literature, which is the diffusion rate of the toluene in silicalite 1. So this term, well, you can do nothing without that. It's imposed by the system. The only parameter on which you can play with, this is the characteristic length. This is, so to say, the diameter of the zeolite crystals, or the thickness of the membrane. And in this case, here you can see that for the platinum silicalite 1 by just inclination, in our system we have, let's say, one order of magnitude in this characteristic length, meaning that we can go from 10 to 1 here. We have plotted the points of the actual catalytic rate, and we see here that in our system we are hardly limited by the diffusion. And I recall you that we have selected this case because we thought it was the worst scenario. So in conclusion, I believe that for this type of materials, we won't be hardly limited by the diffusion because of the so thin layers of the zeolites. As a conclusion, I would say that in my first part, I show how we can use hollow zeolites as a nanovessel to make nanoparticles of control size and control surface composition. And in the later, I show you how we can use these nanomembranes in order to add functionality, in order to add separation factors and selectivity in oxidation or hydrogenation or even Fischer-Tropsch catalysis. I would say that despite so many advantages, I don't think I will see one day this system widely applied in the industry. There are many reasons, but one reason is the density of the metal particle per unit of volume, because it's just void, I would say. If you would fill a reactor with those hollow zeolite, you have it's just air, it's empty. So one way to do that, or to overcome that, is to increase the metal concentration per unit of volume. So you can take a larger crystals and make more cavities per crystal, if you want, like here, and load the cavities per particle. But in this case, we lose a bit control of the size of the cavity, meaning we lose also the size control of the particle. Another main avenue we want to explore is to add a catalytic function to the zeolite membrane. And this can be achieved by adding aluminum in the zeolites and yielding here ZSM5. And you can see here pictures of platinum nanoparticle encapsulated in ZSM5. We're going to apply that for bifunctional catalysis, obviously. And here at the bottom, you can see that we are very recently achieved to make hollow beta zeolite that will be applied also next in catalysis. With that, I would like to thank my collaborators, Dr. Alain Thuel, who is mastering these zeolite nano particles, and also Dr. Shiwen Li. So Shiwen is obviously from China. She came at Lyon with a CSC grant, and she did most of the work on the nanoparticles. I would like also to thank PhD students that are today working on the same topic here, and the colleagues in my team, Schurman, Meunier, Morfin, and Rosset from the IRSE Lyon. I would like also to thank the European community for supporting this study. And again, I thank the organization committee and the IACS members, including Professor Corman, and I would like to thank you for your kind attention.